Welcome, guys. So today we are just trying to use the Cauchy integral theorem to prove these Morera's theorems. Okay, so apologize for my pronunciation. So if a function f of z is a simply in a simply connected region R, so simply connected means there's no holes, right? If you're more like the abstract mathematics, then you can prove. You can show this is the good way to see that the fundamental group, the fundamental group of the R is 0. So basically each cycle can be contracted as empty, as a 0, right? Or then if you have a f of z dz along C is 0 for every closed contour C within R, then f of z is analytic through R. Okay, so this is a statement of theorem. Okay, so let's see the proof. Okay, let me change the background to color. Change the background color to black because I like to use black. Okay. Okay, so the proof. Suppose we start, let's say f of z, and then we start from z1 and z2. Okay. So let's say see what to do. Okay, so we know that the c f of z dz is 0, right? So basically, this means that if this is c1, this is c2, then c1 f of z dz will as the same as c2. So that means f of z integration along z1 and z2 is independent of path. Okay, so that means I can write f of z. I can write this as large f of z2 minus f of z1, right? Because I know that what is the this is so I can define large f to be this way because which is independent of path. Okay, so that means I can divide it z1 and z2, z1 minus z2, right? So z2 minus z1 as this f of z dz z1 z2. Okay, and let me just write it as this way. So let me just write it as fz2 minus fz1 z2 minus z1 minus s small fz1. Okay, so this is z2 minus z1 z2. So f of t minus f of z1 dt1. Okay, so what you see? So I think everyone knows about this, right? I just changed t z to t, the first term, and the second term is just constant, and so basically when you integrate this f of z1, you get z2 minus z1, so this cancels. So we have this identity. Okay, so we can take a limit as z2 approach to z1, right? As any directions, right? So so basically remember that the function limit exists if z2 goes to approach to z1 for any directions. Okay, so let's take z2 approach to z1. Right, and this term will be 0, right? Because the integral upper bound and lower bound will be 0. So finally, what we get is z2 approach to z1, f of z2 minus f of z1, z2 z1 minus z1 equals to f of z1, right? And now, so this limit is this. So this is just f prime of z1 equals to f z1. So that means f prime exists. Okay, so so this shows f prime exists. F prime limit for any points inside R, the derivative exists, right? So f is analytic. So remember this is the definition of the analytic, right? A function analytic if the function of analytic means that its derivative exists everywhere. So now its derivative exists everywhere, right? By our definition. So f is analytic, so f prime is analytic. So this is the complex analysis results, and this is what we want to use the Cauchy theorem, right? But we know that Cauchy theorem tells us that the derivative of f10 f prime 0 is just 2 pi I f of z minus z0. Okay, so this I should say square. Okay, so this tells us that f is analytic. Okay, well implies that f prime is analytic. So this is prime. It's analytic. And by definition, what we already show is f is analytic. Right, so f prime, which is f, is analytic. And so this is what we want. So f is analytic. Okay. So the proof is very simple, that we just use the independent of the path, and then we can do this. And I think what we want to do for the what we want to do without this pole, because otherwise that you cannot use this theorem, right? If you want to use this theorem, you need to ensure that z0 is inside the region of what you choose. And also, if you have a hole, then I think the right, if you choose things on this, right, if you choose points on this, right, then you cannot approach these points from these directions. So we need to assume that there's no hole. There's no hole inside the region. Okay, this is a trivial group. Okay, never mind. Okay, so this is the Morera's theorem's proof. Basically, that's it. So basically, we start from independent paths, and finally we use the Cauchy theorem. So we use Cauchy theorem only on this part, right? F is analytic, f prime is analytic. So large F is analytic, so f prime of f is analytic. And next time, I think comparison analysis is already over, right? The important point. So next time we will prove the Duvernier theorems and the fundamental theorem of algebra using the complex analysis. Be sure to subscribe to my channel. Thanks.